Hello and welcome, fellow students. Today we're going to start a lecture about the accessibility matrix of a graph, and specifically a directed graph. So stick around and enjoy yourselves. And this is the problem that we must solve today, right? We need to write the accessibility matrix of this directed graph. To do so, we will start defining what is the accessibility matrix, right? So let's call it M of a directed graph, right? Accessibility matrix, or better, M of a directed graph is a matrix where the element M sub ij is equals to 1 only if the vertex vj is accessible from the vertex bi. Right, so this is the accessibility matrix. For instance, if I can access from 1 to 4, right, and I can do it following this path, I could put a 1 in the position 1, 4 of that matrix. So that is how it works. It doesn't need to be a direct access, right? Of course, 3 is accessible for 1, but it can be also accessible from a path of any length, right? So this is mainly the difference with the adjacency matrix, because in the adjacency matrix, we put a 1 in that position only if the path is of length 1, right? If it is the adjacent node, which is accessible. But here is for a path, if it is accessible for a path of any length. And in fact, we are going to define the accessibility matrix of order key, sorry. We call it M key of a directed graph. And it is a matrix where the element ij is equals 1 only if the vertex vj is key accessible from bi, right? So that means that there is a path of length key from b1 to bi to bj. Right, so these are the definitions that we need for this problem. Right, so there are two ways of calculating this matrix. One is the direct way, right? We can come here to the graph because this is a very small graph, and we can say, okay, we start by the node 1, and the node 1 is accessible from 1, right? Because a node is always accessible from itself. So in the position 1, 1, we put 1. 2 is accessible from 1, right? We can go directly from 1 to 2. 3 is also accessible from 1. And 4 is accessible from 1 through 3, through 3, right? So we put 1 here. For the second vertex, 1 is not accessible from 2, right? There is no way of going from 2 to 1. So we put a 0. As you can see, 1 does not have any input link. It only has 2 output links. So it won't be accessible from any vertex. The vertex 2 is accessible from itself. 3 is accessible from 2, and 4 is also accessible from 2, right? We can go from 2 to 3 and then from 3 to 4. Then we pass to the vertex 3. From 3, we cannot go to 1. We can go to 2 through 4. We can go to 3 because it's the same vertex. And we can go to 4 directly. And finally, in 4, we cannot go to 1. We can go to 2. We can go to 3 through 2. And we can go to 4, right? So this is one way to calculate let's call this graph D. So this is the accessibility matrix for D. Okay, so in this case it was easy because this is a very small graph, right? We only have 4 nodes and a few links. But what would happen if the graph was bigger or more complex? Well, in that case, there is another formula to calculate the accessibility matrix, right? And in this case, the accessibility matrix of this graph is equals to the identity matrix. The identity matrix is the one that has ones on the diagonal, right? It has ones on this main diagonal. And then we need to add the accessibility matrix of order 1, the accessibility matrix of order 2, and the accessibility matrix of order 3. Why of order 3? Well, because we only have four nodes in the graph, right? I will let you think about it. Think why we only need to add until the accessibility matrix of order 3, depending on that we have 4 nodes in the graph, right? So that means if we have 5 nodes, we would need to add also the accessibility matrix of order 4. If we have 7 nodes, we would need to add until the accessibility matrix of order 6, right? And like that. And it's good if you think why. I will write it here. We have 4 nodes in the graph. Now, what you have to take into account is that this addition is the logical addition, right? So it means that we put a 1 in the result if there is a 1 in any of the previous of the 2 matrices that we are adding, right? So if there is a 1 in the position 1, 1 of any of the 2 matrices, we would put a 1 in the result. So it's more or less like an OR, right? This addition is like the logical OR. And then how do we calculate these accessibility matrices, right? There is also a trick, right? A trick to do so. And let's see it, okay? So let's start by the accessibility matrix of order 1. So this will be similar to the adjacency matrix, right? So that means that I need to put a 1 on the positions where I have a path of length 1, right? From one node to the other. If I start in 1, I don't have a path from 1 to 1. I do have a path from 1 to 2, right, of length 1. I have a path from 1 to 3 of length 1, and I don't have a path from 1 to 4 of length 1. If we check the second node, we only have a path to 3, right, of length 1. So I don't have to 1, I don't have to 2, I have to 3, I don't have to 4. If we check the node 3, we only have a path of length 1 to node 4, right? So I don't have to 1, I don't have to 2, I don't have to 3, I do have to 4. In the node 4, we have 2 paths, 1 to 2, right? So 1 to 2, and the other to 4, right? And I'm done, right? I finished. So this is the accessibility matrix of order 1. Now, if you want to calculate the accessibility matrix of order 2, you have 2 options, right? You have 2 options. You can do it as we have done right now, right? Checking the possible paths of order 2 from any node, from every node. Or you can do it with this formula, right? The accessibility matrix of order 2 is equals to the logical multiplication of of 2 accessibility matrices of order 1, right? So it could be something like this. Well, it's sometimes it will be easier to do it like this, right? Because now it's with the first matrix, it's not so difficult to calculate the path of length 1, but later, if we have bigger matrices, it can become more and more complex. Okay, and how do we calculate this multiplication? right? So this multiplication, the element mij of one matrix is equals to the row I from the first matrix multiplied by the column J from the second matrix. Well, in this case, it is the same matrix, right? We have in both places the same operands, the same matrix. So it will be the row I multiplied by the column J. So for instance, if we have the first position, right, of the matrix, the position 1, 1 will be the row 1 multiplied by the column 1. And this is the same as the first row, which is 0, 1, 1, 0. Multiplied by the first column, which is all zeros, right? It's something like this. And sorry, this is not equals, this is multiplied. And the way, right, the way of doing this multiplication is term by term, right? So we multiply 0 by 0 plus 1 by 0 plus 1 by 0 plus 0 by 0, right? So this is the multiplication of the first row by the first column. And in this case, the result is 0, right? It is 0. Let's do another one just to see a different result, right? So for instance, the position 1, 3, right, which is equivalent to the first row multiplied by the third column. Okay, and this is the first row, and oh no, and the third column is 1, 1, 0, 0. Okay, something like this. So if we multiply these values, let's see what we get. Right, let's see. Okay, so in this case we have 0 by 1 plus 1 by 1 plus 1 by 0 plus 0 by 0, right? And in this case, as this is the logical addition, right? Well, it's enough with having one of the summands where we have two ones, right? So because of this term, the final result will be 1, right? Because we are not multiplying by 0 in that case. You have to take into account that we are doing logical operations here, right? So that means that even if we have all ones everywhere here, the final result would still be 1, right? Because we only want to specify yes or not, right? Is one vertex accessible from other? Yes, it's a 1. No, it's a 0, right? This is the only result that we will have on these matrices. So we can do the next one, right? M2, just multiplying M1 by M1. Okay, in this case, the first row by the first column is 0. The first row by the second column is 0 also. The first row by the third column is 1. And the first row by the fourth column is also 1. Right? So how I did it? Well, the first row multiplied this row by the first column, by the second column, by the third column, and by the fourth column, right? These operations are very easy to do because you only have to put a 1 when there is a match, right? For instance, here, in the last position, we are multiplying the first row by the last column. And in this case, because of this 1 multiplied by this 1, right, we will get a 1 in the final result. So this is the position that we calculated here, M1, 1, and this is the position M1, 3 that we calculated here, right? If it doesn't come out to doing, you know, directly, just do it one by one, right? Just do the operations one by any of the positions in the matrix. We pass to the second row, and now we take the second row and multiply this by any of the columns, right? So this is by the first column, by the second column, by the third column, and by the fourth column. We do the same with the third row. The third row only has 1 at the end, right? So it will, the result will be the same as here, right? As the column where we have 1 at the end. So it will be something like 0, 1, 0, 1. And we go to the final column where we have 0, 1, 1, 1, right? As I'm used to calculate this matrix, I can do it quickly, but as I said, if you need to just make your calculations slowly, right? Making all the operations. Okay, and now, if we want to calculate M3, which is the last one, right? It's the last one. We just need to multiply M1 3 times, right? 3 times. And this is equals to multiply M2 by M1. Right, so now it's a bit different because we need to multiply well, let's do it in order better, right? Let's multiply M1 by M2 because otherwise it will be more difficult. Okay, so you start by the first row of M1, right? First, we take the first row on M1 and we multiply this by the first column on M2, right? This is 0 because we have all zeros. We take the first row of M1 and we multiply this by the first column of M2. And we have a 1 here, right? On this position, so 1. We multiply the first row of M1 by the third column of M2. And we have 0 again. As you can see, these ones match with these zeros here, right? So we have 0 again. Finally, the first row by the fourth column. As this fourth column is all ones, we will have all ones here in the fourth row also. Okay, so we pass to the second row of M1. We multiply by every column and we get 0, 1, 0, 1. We pass to the third row of M1 and we get 0, 1, 1, 1. And we pass to the fourth row and we get again 0, 1, 1, 1. Okay, so this is M3. The accessibility matrix of order 3. Now we need the identity matrix, right, which is the one that has ones in the diagonal. And now the only thing that is missing is to add all of these matrices. Okay, so how do we add these matrices, right? So in this case, the addition of these matrices, let's do M1 plus M2, for instance. This implies that the element IA on the result will be 1 if the element ij on the first matrix is 1, or the element ij on the second matrix, let's put or here, or the element ij in the second matrix is 1. Right, so that means that we have to check all the matrices, and if in the first position of any of them there is a 1, it means that in the accessibility matrix there will be a 1. Why? Because this matrix means that there is a path of length 1. This matrix means that there is a path of length 2. And this matrix means that there is a path of length 3. And of course, this is the identity matrix, which means that every node is related, is linked to itself. It's accessible from itself. So if there is a 1 on any of these positions, we put a 1 in the accessibility matrix. So let's do it here. Okay, let's write it here. For the first position, there is a 1 on the identity matrix. For the second position, there is a 1 on M1. For the third, there is on M1. For the fourth position, there is on M2. Here, there is a 0 in all matrices. Here, there is a 1 on M3. There is a 1 here on M1. And there is a 1 here on M2. Here, there is a 0 on all matrices. There is a 1 on M2, a 1 on M3, a 1 on M1, 0 in all matrices, a 1 on M1, a 1 on M2, a 1 on M2, and we finished. Right, so this is the accessibility matrix calculated with the formula. And as you can see, it is the same as the matrix that we calculated at the beginning. Right, so that's all on this exercise. I will let you a couple of seconds to copy the exercise, and then I will stop sharing the screen. Okay, so thank you for joining me on this lecture. As always, if you have any doubt, any question, if you have any error, any mistake that I made in the lecture and you want to let me know, please write it down in the comments, right? Or if you have any doubt that you want to ask, don't hesitate to write down in the comments. That's all for today. Thank you for joining me, and I will see you in the next lecture. Ciao, ciao.